Well, welcome to your first lesson in our AP Calculus series. Congratulations for making it this far, and we are hoping for an amazing year together. So I found this picture, and I hope this is what you're coming to class with every single day. Because all this kid is saying is there ain't nothing I'd rather be doing than calculus. And this is the kind of energy and attitude we want to see with you every single day this year. So you've guessed it, we are taking it to the limit tonight, and we are going to talk about finding limits graphically. So in part of this flipped classroom, it requires a lot of you taking your own notes. So of course we want a title, finding limits graphically, and the date. So I think it's safe to say no matter where we're coming from, we've all talked about a limit in a graphical form. But let's get this definition clearly written out. A limit is as a function gets closer and closer to a certain x value, what is the intended height? And you'll notice I have this capitalized, and perhaps we should even underline it. That's all we're talking about when we mention the word limit, the intended height. We don't care if it actually gets there, but what are its intentions? Now, not only do we have to analyze this graphically, we also have to talk mathematically correct. Okay, so we're going to get this notation again written out in your notebook nicely, and we're going to put it in English and talk about how we want to read this out loud. And in fact, in class tomorrow, you're going to have a lot of reading out loud. So this is called a left-handed limit, and you'll notice it's left because of this negative sign. So this is read, so get your notation down. The limit, that's the LIM, as x approaches, if it helps, the approaches is the arrow. So as x approaches c, the negative is telling me from the left of f of x. A right-handed limit, again, is going to be the limit, there's my LIM, as x approaches, that's the nice arrow. What is it approaching? Well, c with a plus means c from the right of f of x. And lastly, we would call those one-sided limits, and then we have what we call the general limit, the overall limit. Notice this does not have a plus or a minus, so this is just read the limit as x approaches c of f of x. So our next piece is a limit exists if and only if, and here's what we have to have jotted down perfectly. The limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x. Okay, so you can box this in. You can expect to see this on every quiz that we do. This is the definition, a limit exists. So don't be afraid to grab your highlighters. This is a good time to start highlighting things. For a limit to exist, the left side has to meet the right side. They have to have the same answer. If this is 2, then this needs to be 2. If this is 5, then this is 5. If they're not, then we would say something like the limit does not exist. So again, maybe you can relate back to this movie. Maybe I'm dating myself a little bit, but Mean Girls. If the limit from the left does not equal the limit from the right, then we conclude the limit does not exist. We also want to make sure we cover what a continuous function is. So again, as a definition here, a function is continuous if it has no breaks or gaps in its graph. Basically, you can draw it without picking up your pencil. Now, I just want to be clear, this isn't like an actual definition that I would use when talking to another mathematician, like yourself. However, this is kind of like the little kid version, and we're going to start with that and work our way up to the mathematician definition. But hopefully you're thinking to yourself, okay, it has no breaks or gaps in its graph. So something like this that I can draw without picking up my pencil, that is continuous. You saw me draw it, I didn't pick up my pencil. But if it has a break, so maybe I go like that, and I pick up my pencil and I restart it over here, it has a break. So I would say this is not continuous. And that's as simple as I want you to think of it for now. Now, the AP does say you have to understand the difference between a removable discontinuity and a non-removable discontinuity. So it's a big deal that we get these straightened out in our notes and in our heads. So you'll notice a removable discontinuity basically has a hole in the graph. So again, I'm going to call that a hole. And it has a hole in this graph. Okay, and that is called a removable discontinuity, a hole in the graph. So one way I like to think about it, and don't put this in your notes, if I were to take my pen and just fill in the hole, it now becomes a continuous function. So if I can fill in the hole with one little speck there, it now becomes continuous. Like I said, do not fill in the hole in your notes there, but that's what I'm thinking. A removable is a hole, and one little dot there should make it continuous. A non-removable is going to look something like this. This has a vertical asymptote, and this has what we call a jump. Okay, and why are they non-removable? Well, if I put one dot here, if I were to fill this in, so let me go ahead and do it, don't do it in your notes, but if I were to fill that in, is this now continuous, or do you have to pick up your pencil to draw the second half? Well, notice I had to go from here to here, and then I had to pick up my pen and draw this. So when I put that one dot in there, it did not become continuous. Therefore, it is non-removable. Same idea here. If this gets closer and closer, and this gets closer and closer, and I just put one dot, it does not make it continuous all of a sudden. So anytime there is a hole, it's called a removable discontinuity. Vertical asymptotes and jumps are non-removable. All right, so you're going to have to pause it. You're going to need to sketch this perfectly in your notebook. Every now and then, some kids like to kind of freeze frame it and print it and put it in their notebook. That's completely up to you when we have all these graphs, but these do need to be in your notebook. So pause and do what you need to. Turn it back on when you're ready. So our goal is to evaluate many different functions here. So we're going to start with this first one, using this graph called f of x. So I'll just go ahead and label it f of x. I'm going to start with this first piece. What is the limit as x approaches negative infinity? So here's the deal. Because it says x approaching, you're going to go to your x-axis. It says negative infinity, so I'm going to go way out here. I'm going to pretend I can go out further. Negative infinity on the x-axis is over here. And you find the graph closest to it. Well, would you say this graph is closest to negative infinity? I sure hope not. Negative infinity is over here, so this piece is the closest to it. And basically, remember that arrow means approach, so approach negative infinity. Go out towards negative infinity. And limit, recall, means the intended height. How high can this graph ever get? Well, do you see this asymptote here? It's not going to go past it. It's going to get closer and closer by definition. So I'm going to say that limit is a positive 3. The limit, I'm going to go down the column here. The limit as x approaches negative 5, and notice this negative, so that means from the left. Okay, so I'm going to go to the x-axis, I'm going to go to negative 5, so I'm going to start at negative 5 on the x, and I want to find the graph on the left-hand side. So here's my negative 5, this is my left, this is my right. So I'm going to go to the left-hand side of negative 5, and remember that arrow means approach. Approach negative 5. What is the intended height? It's intending to get to a height of 1. Okay, so let's try negative 5 from the right. So I go to x equals negative 5. I approach it from the right-hand side. So here's my right-hand side. This piece of the graph is closest. Approach means go towards. I'm going to go towards negative 5, and the graph is taking me to a height of negative 2. Now, this last piece you'll notice is a general limit. It doesn't say the left or the right, which means I have to compare the left and I have to compare the right. Are they the same answer? Well, no, they're not. One was 1 and one was negative 2. So I'm going to say DNE, the limit does not exist. Okay, hopefully you're feeling okay with this. Let's try another one. If not, that's okay too. So this time I want to approach 0 from the left. So I'm going to the x-axis of 0. I'm going to approach, I have to go towards 0, and I would say this graph is on the left of 0. As I approach from the left, I'm intending to get to a height of 4. I'm going to approach 0 from the right, so here's my right going towards 0, approaching 0. Again, I'm intending to reach a height of 4. If the left side and the right side are the same, then the general limit is 4. Well, the same answer. Let's try negative 2. As I approach negative 2 from the left, I'm sorry, not negative 2, positive 2 from the left. So here's positive 2. Coming in from the left, I'm approaching 2 on the left-hand side. It looks like I'm getting to a height of 0, intending to. As I approach 2 from the right, again, I'm intending to reach a height of 0. Therefore, my limit is 0. Now, let me ask you this question. Let's go ahead and add this on. What if I asked you what is f of 2? What is f of 2? Well, at 2, the answer is not 0 because it's open there. The answer is actually 5. So what is that telling me? Well, the function's limit exists, but it's not continuous. Okay, I want to go ahead and make a note here. There is a hole at x equals 2. Therefore, this graph is not continuous. Let's go ahead and try 5 from the left. So if I approach, here's 5 on the x-axis. If I go 5 from the left, it looks like this graph is headed up towards positive infinity. If I go 5 from the right, it's headed down towards negative infinity. Therefore, my limit does not exist. And lastly, what is the limit as x approaches positive infinity? So I'm going to go to the x-axis. I'm going to go out to infinity, which would be way over here. This is the graph closest to it. And as I approach it, as I go out towards infinity, this graph is heading down. So I would say its limit is negative infinity. All right, in example number 2, again, I'm going to need you to pause it and copy this graph down perfectly. And then we're going to go ahead and answer these questions. Now, in a flipped classroom, guys, the only way you truly get an understanding is if you pause it and practice. Okay, and it's very obvious in class of those of you that don't pause it. Okay, so let's make good decisions from the beginning here. You need to pause it. And what I want you to do is try all of these on your own. Okay, and when you're ready, you can hit play and all my answers will appear. And then if you're good and you don't have any questions, you can kind of skip to the next part. Otherwise, I'll explain it out for you. Okay, so this is your time. Pause it and try these on your own. All right, so like I said, here are my answers. If you're good, feel free to skip the next few moments and just kind of scroll along. If not, I can quickly talk about where these came from. So again, as x approaches negative infinity, I go out to negative infinity. Approach means go towards it. This is the piece that goes towards it, so it's heading towards infinity. Negative 3 from the left has an intended height, if you follow my arrow, of negative 2. Negative 3 or positive 2. Negative 3 from the right also has an intended height of 2. Therefore, the overall general limit is 2. Negative 1 from the left is heading towards 0. From the right, negative 3. Therefore, the limit doesn't exist. 2 from the left is negative... 2 from the left, I'm not even following 2, is negative infinity. 2 from the right is positive infinity. Therefore, the limit does not exist. 5 from the left is 2. 5 from the right is 2. Therefore, the limit is 2. And if I go out as x approaches infinity, there's an asymptote, so I'm getting closer to a height of 1. Okay, now for the truly fun part. If you really understand limits, this is actually kind of fun to do. So we're going to take our time and I'm going to kind of show you some methods that I use. So they're going to give us a bunch of characteristics of a function, and our goal is to graph this function. So the first thing I kind of do is I look for the really easy pieces. For example, f of 0 is 3. So that's the point 0, 3. And I'll plot that point. Another easy one, f of 3 is 4. So 3, 4. Okay, so there's an easy one. And I think that takes care of the easy ones. Okay, so you'll notice that these 3 pieces all deal with a limit as x approaches 0. So I'm going to go to the x-axis, I'm going to go to 0. And it says when I come in from the left, my height has to be 5. So here's what I do. I find 0, I go up to 5, and I make an open circle with a tail from the left. Now I don't, draw too much on this side yet. I just make a little tail, and you'll see why in a minute. Now you might be saying, well, why did you not make a closed circle? Well, think about this. If this is closed and this is closed, you're not a function. Okay, so the only time you ever close something is if you know it's completely true, like it's an exact point. So I'm going to check off that we did that one. If I come in from 0 from the right, so when I come in on this side, I have to reach a height of 3. So I'm going to go to 0, 3, and on the right-hand side, I'm going to make a tail there. Okay, so check. Now, does it make sense that the limit doesn't exist? Well, of course it does. The left side did not equal the right side. Okay, let's go to the next piece of information. The limit as x approaches 3 equals 2. Now hold up, why didn't they tell me the left and the right? Well, they don't need to. If they're telling me the general limit is 2, remember that means the left side must equal the right side. So as I go to the x-axis at the number 3, the left side and the right side are hitting from a point of 2. So my intended height on the right side and the left side are 2. Now remember, I'm always putting an open circle unless I know it's an exact point. All right, the next piece says these are all about -2. As I approach -2 from the left, I need to shoot towards -infinity. So here's -2. When I come in from the left, I'm going to be going down forever. So I kind of just make an arrow going down. So check. When I approach -2 from the right, I'm going to go up forever. So I'm going to make an arrow going up. What do you think you just created at -2? Hopefully I heard you correctly, and you said a vertical asymptote. Okay. And that checks off that the limit does not exist. And lastly, the limit as x approaches infinity. So if I go way out over here, I'm approaching a height of -2. Okay, so if I go way out, my height's only going to ever reach -2. So can you guess what you created there? A nice horizontal asymptote. And as I approach -infinity, so as I go way out over here, my graph is shooting towards positive infinity. Oops, I'm just going to do that in red since everything else was in red. Okay, so now all I do is I kind of connect the tails. I say, okay, if this tail was going to connect with a graph, it's not going to connect with somebody over here, it's going to connect with the closest one to it. Who's closest to this guy? Well, hopefully you said this one, so I'm just going to kind of connect those. Okay, so now I'm just going left to right. So I got those pieces. Now here's the next piece on the left. Who is this tail closest to? I can't skip anybody. I can't jump way over here because I'm skipping these guys. It's closest to that tail. So I'm just going to loop those together. I'm going to say, okay, who's this tail closest to? Well, it's closest to this tail, so I'm going to zip those together. And then this tail is closest to this tail, so I'm going to zip those together. And there you go. We have created a function that had the following characteristics. Now remember, the flipped classroom is awesome because the power is in your hand. If something misled you there, pause it, rewind it, and go back and watch it again. So lastly, I just want to talk about the discontinuities that this graph has. Clearly, it's not continuous. I can't get from the left-hand side to the right-hand side without picking up my pen. So our choices are removable or non-removable. Remember, removable meant if you put in one dot, it now makes your function continuous. So I'm going to make a note. I would say if I were to fill this in, would you agree this piece would be continuous if I fill that in? And because this is a hole, remember that's called a removable discontinuity. You'll notice if I were to fill in this dot here, could I draw this whole thing without picking up my pencil? Heck no. So this is a jump, which is a non-removable. And same idea here, if I were to put a dot, I would not be able to draw this with one swoop of my pencil. So this asymptote, vertical asymptote to be specific, is a non-removable discontinuity. Well, that does it for us tonight, and I look forward to some great practice tomorrow. So remember, I'm always here in the morning. Feel free to come find me if you have any quick questions.